Hi student who is attending this class, and hello audience who will be watching my video later on. Okay, this is the beginning of this semester, and this is the series course of one course of power electronics, and the title of this lecture, official lecture, is Power Conversion Circuit, but in here written as offline flyback converter and DC power systems. So technically this is the correct title of this lecture, but I'll explain the background of this. They don't comparable with each other. Offline flyback converter is just a single converter, and DC power distribution system is collection of converters. So there is a reason why I select this strange the title name. Okay, and first of all, I'd like to mention several things, and we are taking video now. And after this lecture, 1 or 2 days later, I'll post this video and post lecture slide. You have lecture slide, that is the pre-lecture slide, and I'll make some note on the lecture slide, and the complete lecture with all notes will be posted along with the lecture video. Okay, and the lecture video will be posted in 2 different channels, places. One is my homepage, the other one is YouTube channel I'm running. Okay, so either of them is okay. Okay, complete information about this lecture will be posted there. Okay, but there is just some delay. In OCW side, my homepage will be posted at the same day of class, but the YouTube channel will be delayed 1 day or something similar to that. Okay. And one very important announcement is there is a changes in classes. I have some personal plan appointment made long time ago. So this class, actually 2 weeks, I'll be out of town. Okay, let's not. Okay. So November 18th, 20th, 25th, 27th, class will be moved to December 9, 11, 16th, 18th. Okay, I'm sorry we did this, but I should go somewhere else, okay, to teach something, power electronics to some other student. Okay, so I made a contract with them, so I should go there. So we don't have a class for 2 weeks, and this is the end of semester. There is just some period for the makeup classes, and during that period of time, you will have the additional 4 classes. Okay, so you are not losing anything. All right. Okay. Okay. So, and this is the title page, and this picture is taken the cover page of my book. Okay. So I'd like to explain the background of this title, some strange lecture title. Okay, this is my publication. Okay, and this is the second edition. I published the first edition about 10 years ago, and maybe 3 years ago I published the second edition. So this is the second edition. Okay, the content is very good, excellent. One bad thing is it's very expensive. I don't know why. So nobody will buy it. Okay, very little people, very small people bought it, and not anymore. Okay, so but it has a comprehensive information about the power electronics, PWM, power conversions. Okay, and I classified this into 19 topics. So this is 19 topics I classified. So topics on PWM converters. Topic 1, PWM power conversion, some introductory lecture, very short lecture, and so on, so on. So over the years, I taught these courses one by one, and I posted in OCW site, my homepage, and YouTube channel. So in the previous semester, I lectured this topic 9 and the topic 10, and this is directly related with topic 10. Topic 11 is very practical application of current mode control to offline flyback converter. Okay, if we go industries, maybe 99% of the power supply they are making is this offline flyback converter is very popular. Okay, because this is very cheap, very cost effective, and very handy. Okay, so this is very important. So in the previous semester, I intended to cover this, but somehow I failed to cover this. Okay, so this semester start with this topic 11, but their goal of this lecture, their objective of this lecture is to cover this power system issues. It start from the topic 12, okay, DC power systems and uncoupled converter, and something related with the system issues, power systems. Okay, you have, the PWM converter is standalone converter. There is one source, there is one converter, and there is one node. Okay, that is the previous teaching. Okay, and now they connect them together. They have some strange combination of parallel connection or series connection, cascade connection of many converters, inverters, and other DC sources or AC sources. They call the system. And if you consider your power system only deals with DC or mainly DC, it's called the DC power distribution system. And in the system, there are many converters connected all together, and we treat each converter as a subsystem. Okay, you are not paying attention on the inside of converter, just very little, and most of our interest is the system issue, the interaction between subsystems, converters, and the system stability problem, comparability problem, and the performance prediction, evaluation, and improvement. Okay, that issue will be covered here. So this is a very new topic. Okay, in the past there are some guys studying this here and there. Okay, individually, and they published, including myself, some papers. But I reorganized this, and I developed this story, one coherent story, and to my knowledge, this is the first time to present this topic in this manner, in this systematic manner, in a textbook format. It's the first time. Okay, so we'll cover this probably. My objective is to cover this, and this 6 of them, something like that. But this is a very aggressive target. So I'm not sure. Maybe this topic 16 is in doubt. Okay, maybe we quit somewhere here, something like that. Okay, so we start out here. Okay, actually this belongs to this. Okay, but we start out from here. Okay, so this is the story about this. Okay. Go back to the previous lecture. So in this book has 4 parts: part 1, part 2, part 3, and part 4, something like that. And part 3 is dynamics and control of PWM converters. Part 3. So we take one chapter here, which is chapter 8, and part 4 deals with the DC, power distribution systems. And in part 4, we take 3 chapters, 9, 10, 11. Okay, so this is from chapter 8. This is from chapter 8. This is chapter 8. And from chapter 9, we have 2 topics. This is from chapter 10 and chapter 11, something like that. Okay, so this is the story, or the past history, and the way we are going. Okay, after this semester, maybe I'll be discussing this. Okay, then my time here will expire, so I'll be gone somewhere else. Okay, then no more teaching here. All right. Okay, and this is kind of syllabus, and the important information here is, this is a homepage address, eeclassroom.org. Classroom indicate, implies electrical engineering classroom, online classroom. Okay, and the YouTube channel, the name of the channel is, this is my name, Byung-cho Choi, Byung-cho Choi. Okay, and if you have time, you read this, and this is the official textbook, but you don't have to buy this. Very expensive, $150, something like $150, something like that. In Korean won, 20만 원, something like that. Nobody will buy it. Okay, I didn't buy it. I won't buy it. Okay, and grading policy, we have one test and one exam. Will be the in-class test or take-out exam. Somehow I prefer take-out exam. Okay, okay. But some case I need to have one in-class test or exam, and this will be 45 to 80% each of them. That means this can be 100% or 90%. Then remaining, this one 10% or 0% will come out from this homework and attendance. Okay, so try to be here on time. All right. So we don't have very little student. So if the number of students decrease, I'll get depressed. So try to show up on time. Okay, don't be late. All right. This is the cover page of the textbook. And I uploaded this, the file name is, the name of this file is first class zip. If we open that file or unzip that file, you have this. Okay, this is long. There is no compensation. All right. So these are PCM files. This is with this green icon is PCM files. Okay, and this one is, it requires professional version of PCM. Okay. Other than this, they are running in license-free student version, free copy PCM. Okay. That's the reason why I select PCM as the software of this class. Okay, and this is the execution file, PCM. This is the license-free copy. So you are free to download this and copy, and you distribute this among your student. That's fine, your friend. Okay, this is, they're encouraging of doing that. Right? This is a very old one, and this company is sold to another company. Previous, the owner of this program was PowerSim, is sold to other company, and they changed something. All right. So you are very good at the downloading something. Then you can use the update version of this. Otherwise, you execute this, then this is good for all of these. I'm using this, and I'm using one professional version, this one, which is very old. Okay? Still, I'm using this, they're fine. All right? Problem is from the student, not from this program. All right? So program is limited in some sense, but they didn't improve that at all. So everything remained the same, and they decorate with something. They sugar coated, okay? But basically they are same thing. The problem remains the same, okay? So you have problem with this old version. You will have the same problem in new version, okay? So use this, okay? Possible. It's free to use this program or any other program of your choice. But this one is very easy to use, okay? I don't like this software that much, but I like the feature. It's very, very good for the teaching. Okay, program looks like the circuit diagram itself. Okay, and this is the lecture slide set. So you download the first set. Previously, I displayed the pre-lecture slide of one semester in advance, but I'm defining my lecture slide all the time. So actually the lecture slide you are having is different what you are going to see today. I modified something. I'm doing that all the time, okay? Every day, okay? So this morning I changed something, okay? But it's not major change, so you are okay now, okay? So I decided to upload this weekly, okay? Over the weekend, I'll upload the next week's post-lecture slide. All right. So in that manner, I minimize you minimize the confusion. Okay. If I dispute all the post-lecture slide for one semester, there are many changes. Okay. Eventually, right. Okay. So I'm updating my lecture slide all the time. Sometimes I add some pages, and sometimes I collect some minor mistake and the typos, and I define my drawings, something like that. And this one, textbook excerpt. My pronunciation, okay? Excerpt, something like that, okay? This is the selection of book material, okay? So this contains all the chapters you need for this class, okay? I'm the author of this book, so I have the PDF file, pre-print PDF file. Okay, before sending the publisher, I made my own PDF, so that is mine, so I can distribute to my student. Okay, so if you open here, there are 4 chapters of this. Okay, for free. Okay. You can pay me if you want, right? Okay. But nobody wants to pay me, okay? All right. This is the, what is this? Portal page of my homepage, EE Classroom. This was me maybe 3 years ago, okay? And this is my business card, and this is the 4 books I published during my life here at KNU. And they are very similar, but they are different. Okay, you don't have to buy this. Okay, so you are using this, right? And this one, this logo, and this logo has some special meaning. Okay, I'll explain this later. That is directly related with the system analysis of DC power distribution system. This represents some interaction between subsystems. So this is the actual impedance plot. Okay, so that is very important, and I'm very proud of this. So I'm using this as often as possible in my business card and in my this one, and I'm using this as the watermark of all the videos I generate. Okay, so if you see this, think about me. This one. Okay. Okay, so how to use this, how to access this will be explained in the next class. Next Thursday, I'll explain this with some example, and you need to visit here to get some the background information, fundamental about the PWM DC power conversion. If you are not quite familiar with now, okay, then anytime you can go back to this EE classroom, or you can go to this YouTube channel, Byung-Jo Choi, and this is classified as playlist. So I have 82, 83. Okay, I'm uploading one or two, at least two videos every week. Okay, so this number is increasing, and you know the playlist. Okay, playlist is just a collection of the videos under the same subject. So this is about the resonant power converters, and the PWM converters has many. This topic, power stage component, current mode controller, so on, and each this playlist contains 7, 8, 9, 10, something like that. Okay, so go here and get the all necessary background information about this. Okay, but this one is all in English. For the Korean student, there are some Korean version. I videotaped for the undergraduate student. So this black one is Korean version. So you can go with this. Okay, then you can pick up some fundamental things about this. Right. So this is about this course. Okay. Okay. So we are moving into the topic 11. Topic 11. Offline PWM converters, specifically flyback converter, with current mode control. Okay, so you should have some basic background about the current mode control and basic background of flyback converter and so on. Okay, small signal modeling and small signal dynamics and the small signal or dynamic performance of converter as a voltage source. Okay, all the background information is available in the OCW site, YouTube site, okay, and my books, okay. But you won't need my books, I know that, okay. Go to YouTube channel and my homepage, okay, if you need some background information. And so in this topic, we'll deal with offline flyback converter, and maybe most of material, not most of, some materials you are already familiar with this because we covered this, some theoretical information. So this can be the theoretical review for some of you, okay, not all of you, for some of you. Okay, that is also important, that is also meaningful. Okay, so we'll move fast in that part. And more important thing is we'll discuss the practical engineering details in practical converter fabrication, design, and fabrication and testing and performance evaluation with PC simulation. Okay, so later part is important, very important. Okay, so we'll review some theoretical aspect of this flyback converter, and I'll provide some new information about the engineering aspect of this practical offline flyback converter. Okay. Okay. Maybe this might be okay. So Sorry, this might be okay. This morning I forgot why I used this term PWM converter. I want to start out from the general setup, okay? Then I go into PWM, the flyback converter, okay? So this is the general setup. So shown here is common structure of offline power supplies. So offline power supply means the input of this system. This is the offline power supply. Input is derived from the AC outlet on the wall of your house. Okay, that is the offline power supply. So this AC 100 volt or 220 volt AC 60 hertz with the maximum value of square root 110 or square root times 220 will go through this AC to DC rectifier. Okay, so this can be simplest possible, this bridge rectifier and some advanced power factor collected circuit rectifier. Okay, either one is okay. Okay, so later on we'll be using simple diode bridge rectifier, and after that we have big bulk capacitor. Purpose of this is to stabilize DC volt. So we are assuming this is the DC and this is the then DC in. Load requires DC, DC in, DC out. So this is the DC converter, and offline converter should provide the galvanic isolation from here to there for the safety. Okay, there's a requirement. So all the offline power supplies should have galvanic isolation in both power stage and controller. Okay, so they are using, obviously they are using transformer here. Now there are some other alternative, but cheapest one and the most popular one is Optocoupler. Optocoupler is 4-port device. Okay, there is a combination of this infrared diode, IR diode. This is a photo transistor, and this diode is generating some invisible infrared light. Okay, so you wanna see this, but this signal is activated this photo transistor. Actually, some photon, I don't know, I didn't see them. Okay, will touch this, will bomb this, then this guy will activate it, will generate some carrier, and the current will flow. That device is called Optocoupler. So they package it in one box together. Okay, 4 terminals is called Optocoupler. It provides very good isolation, 2K volt and 4K volt. But it has some bad things. Okay, some parasitic capacitance will slow down the response time, and there are many alternatives. Some alternative of this. There are some people they are using the optical fiber or something, some strange things. But this is a standard for the consumer electronics, home electronics, because the price is the #1 prime consideration there. Okay, so offline power supplies receives the energy from the utility line, and it consists of DC, AC to this rectifier, and followed by this converter, and they should have this isolation in both power stage and feedback controller, and they should regulate voltage here, because this load can be very sensitive to this input voltage. Then this should be tightly regulated. Okay. So there are many this type of offline power supplies, but basic converter we will be dealing with is offline flyback converter with current mode control. Okay, this page of your handout is different from this one, but it really doesn't matter. Just the title page has been changed. One extra title page has been inserted here. Okay. maybe having one lecture number here is helpful for the student. So in lecture one, we'll talk about the general configuration and the circuit diagram in detail, and I show the experimental converter, so on. Okay, and later lectures will be discussed the details about this one by one. Okay, so this is the functional diagram or simplified circuit diagram of optocoupler isolate offline flyback converter. This is the utility line. So there is the EMI filter. EMI means electromagnetic interface. That is the related with quality of this AC line. Okay, they don't want to pollute this AC line, so there is some requirement. So this power supply should not dump some dirty current here. Okay, I'll explain what is dirty current. Okay, so EMI filter is the different topic. It's somehow remotely related with power electronics. So, but I don't know the details about that. So, but there is just some consideration to block the common mode noise and the differential mode noise. Okay, when differential mode noise is concerned, the structure is the same as the low pass filter, but for the common mode noise, they have something simple. Okay, and effective. So assume this is usually they buy. Okay, there is there are many commercially available EMI filter. They just buy. Okay, then they will provide some isolation, block the propagation noise generated from here to this AC line. Okay, there is electromagnetic noise. Okay, then this is our area. So we have this bridge rectifier, and the CF is the bulk capacitor. It stabilizes the DC value of this. Without this, the DC looks like this. But with this, it is the DC, like DC. Okay, very similar to pure DC. So now we are assuming the pure DC is applied here, and this is a flyback power stage. Okay, and this is MOSFET switch and diode, and this is the current sensing network. So you are using current mode control, and this V lamp is compensation lamp required for the current mode control, and this is the very simple resistor can be used as the current sensing network. We have the details about this in the next slide and next slide. Okay, right. And this is a PWM chip, and this is the compensation lamp, and this switch current is sensed through this current sensing network and combined with V lamp and compared with this V cone. V cone is control voltage derived from this out voltage through this. Okay, this is a voltage feedback circuit, and this circuit provides some feedback compensation, and it generates this current, and the current will generate this signal, okay, IR signal. Then it activates this phototransistor, and this error signal will be delivered to here, and the PWM function will be generated in this block. Okay, all right. Let's take a look at this. Okay, so here we have optocoupler. So this feedback signal is somehow it passing through this. Okay, this is the open collect type. There is no voltage, bias voltage here. That voltage is derived from the output of this. Okay, so it does not require any external DC source. DC source is provided to here, and when this current is going in, this is activated. Okay, this is only 3-terminal device. it has internal reference. This is inverting terminal, and this non-inverting terminal, there is some reference signal, and this open collector type. So this voltage source should be connected here. Then due to this feedback signal, this ID will be changed, will be propagated this, and this optocoupler has two parameters, very important parameters. One is CTR, current transfer ratio between this diode current and this transistor current. It's called the CTO. And unfortunately, it has this parasitic capacitance, very large parasitic capacitance, order of nanofarad. Usually this parasitic capacitor is order of picofarad, but this is nanofarad, so 1,000 times larger than previous one, right? So this has some effect, okay? Actually, it generates the one pole at high frequency, relatively high frequency, all right? And this structure must have integrator structure. So integrator has one pole at origin, and it should provide 1 0 here. So for that, you have some configuration to generate the poles and the zeros, okay? The principle of this is exactly same as the non-isolated controller. Structure of the compensation, 2 pole 1 0, 3 pole 2 0, okay? Some people call it 2 pole 1 0 type 2, 3 pole 2 0 type 3. That is very ridiculous. Then what is type 4? What is type 1? Type 1 is just the integrator. What is type 0? There is a strange terminology. Okay, don't use that. 2 pole 1 0, 3 pole 2 0 is more scientific description. Okay, some strange people, they use the type 2, type 3. Okay, so I'll be using type 6. Why is type 6? Okay, all right. Don't use type 2, type 1. I hate that. I don't like that term. Okay. All right. So this is the peak current mode control. Peak current mode control, optocoupler isolate, feedback controller, and galvanic isolation. In power stage is implemented this flyback converter, because the flyback converter always has flyback transformer. So it inherently has transformer, and it provides this, okay? So that isolation, so this voltage providing this, okay? There is no additional voltage source here, okay? Entirely separate from this side, all right? And in flyback converter, they use some additional auxiliary winding and rectify that voltage, and they are using that voltage for the internal bias of this. Okay, so this is the stand alone power supply. Okay, you don't need any other the DC source to activate this. Okay, everything is auto generated. Okay, so this is some detailed spec and the schematic of this, and the further details is coming later. Okay, so we have EMI filter. We are not interested inside of this, and this is the DC stabilizing capacitor, and this is the flyback transformer, and this is the magnetizing inductance of this transformer. This is used as the functional inductor, so we have no additional inductor here. This inductor is working as inductor in buck converter or any other converter. Okay. And this is the CSN, current sensing network. So this is a low power application. So switch current is passing through this. Okay. And the inside of this NCP 1230 is very famous IC. This is developed a very famous company. Anybody know Basso? Basso guy? He was working the company. Okay. This is very successful. I see many people using this. And all of this is inside of this chip. Okay, so everything is fixed. This is fixed. This is fixed. All right, and the height of lamp is fixed here. Okay, but in the color mode design, you need to have some flexible slope, compensation lamp slope. Okay, but this is fixed. But this voltage will be divided by this one. There is a resistor, and this is very small. Okay, you can ignore this. And then this voltage will be divided by this. You vary this. This is the design parameter. You adjust this. If you adjust this, you are changing the height of this lamp. That means you are changing the slope of the lamp. Okay, so don't say this only provide fixed lamp signal. That's not true. Okay, so they are providing some fixed one, but they are not dummy. So they prepare this. So by changing this, the peak value effective lamp shown here will be changed. That means the slope is changing. Okay, and this ratio of these two resistors is very smart selection. This is the 1, 2, 1. This is the 2. Okay, this is 1/3 of total resistance. Okay, so they prefer this number. All right, so this voltage will be divided by this. Okay, and this then that determines the current through this. Okay, so this voltage here is first determined. It has, okay, let me say this first. So it has this one. This is the voltage division, and this TL431 has internal reference signal, which is 2.5 volt. Okay, so we have virtual short here. So VO divided by these two resistance plus this should be 2.5, okay, because of the virtual short feature of this, and this will provide this the integration structure. So it generates the one pole at origin, okay, and then because of the virtual short, you have this. Then with this number, our voltage is 10 volt. So now VO is 10 volt. So VO is 10 volt. So this output is 10 volt, and IO is this one. This R is varying, okay, and the switch frequency is fixed, okay. For the chip implementation of this IC, so they fixed this, but this one changed. That input voltage, DC voltage will be varied. This is the case of 110 volt AC RMS, and this is 220 volt RMS AC voltage. So input voltage is varying widely. So this is developed for the universal input. So this can be used in Europe, in Korea, in the state. All right. So this is a universal input. Okay. So this is their specification, and usually this converter is in CCM, and sometimes it goes to the DCM, or sometimes it can go to boundary mode operation. All right. So when you are designing for this, there are 4 choice. This one, this one, this one, this one. Which one you select? Which one you select? Okay. For the worst case dynamics comes from this flyback converter has RHP0, which is omega RHP is given by 1 minus D squared times R, and D times N squared Lm. Okay, Lm is this one, magnetizing inductance of flyback transformer. N is turns ratio 1 to N. Okay, so N is very small number here, 1 to N, right? But they are fixed. They are fixed. So this Lm, N is fixed. What can vary is D. D depending on the input voltage value, D, when this is low, D can be maximum, okay, something like that. And R is changing when this output voltage is very high, R becomes small, okay. This RHP0 is creating some problem in the phase characteristics of the loop gain. It becomes more detrimental when appears at low frequency, right? When that case occurs, D will be maximum. This is 1 minus D. This will be maximum when input voltage is low, and R will be small when this load current is high. Okay, so control point should be this one, low line, heavy load. Right? So that is the worst case design. If you select the other point for the control design, then converter could become unstable when the other operating condition. Okay. Another one is the CCM and the DCM dynamics are very different, but worst case occurs at the CCM. You went through that. Okay. We discussed in detail about that when we are talking about the voltage mode control and current mode control. Okay. So the condition, this omega RHP becomes smaller is the worst scenario which occurs at this one, Okay, this should be the design point. That is very important. Okay, that is very important. The easy way of remaining this is this input is very small and this load current is very high, heavy. So the converter is suffering most in this case. This is the most loading case, worst operational scenario, okay, for this converter. All right. So we are extracting maximum out of this converter. The input is very small and the output is maximum. That's the worst case for this converter. Somehow that becomes the worst case for the dynamic property of this converter. Okay? So that is the simple way of remembering this. Okay? So suppose somebody is the minimum, giving the food is minimum and the labor is maximum. That is the worst condition for you. Okay? Same is true here for this power supply. Right? And this, we have this CJ, this parasitic capacitance. It's a combination of the junction capacitance here, and there is some capacitance between this that is reflected by the Miller effect. So there is some multiplication factor of beta. So this capacitance becomes very large. Okay, and this combines with this one, and it produces a pole. Okay, so from this structure, it has integrator and 1, 0. And from this structure, it has additional pole. So this converter, this configuration, as it is, generate what? 2 pole, 1, 0 compensation. Don't call it type 2. 2 pole, 1, 0 compensation. Okay? And everything makes sense. Okay? That all this components are absolutely needed. Without any of them, it don't work. Okay? Then what is the purpose of this? What is the purpose of this? This? Okay. I said this is the open collector type. Then some current must come into the output port of this. Okay? So this current should be sufficiently large, larger than 1 milliamp, for example, 10 milliamp. All right? But without this, this diode current is determined by what? This one? Not this one. Not this one. Okay? First, this voltage is determined first. Voltage here will be determined first to generate the required duty ratio to regulate our voltage. Okay? And that is the principle of negative feedback with integrator structure. So this voltage is fixed to generate this, to regulate our voltage at this value. This voltage is fixed, and this one is also involved with this waveform. Anyway, this voltage is fixed. That means this current is fixed. Okay, this current, because the current times this distance is this voltage is fixed. Then this current is fixed. Okay, then this diode current is first determined. This voltage is first determined here, and then this transistor current is second determined. Then there is a CTR. Due to the CTR, diode current is determined. Okay. For some case, this current is very small, CTR is small, then this current is very small, regardless of this value. Okay. There is the characteristic of this diode. Okay. Then you need some additional current. So this is the 0.1 milliamp. Then this guy should provide 1 milliamp, something like that. Then this current is sufficiently larger than 1 milliamp. Then this chip is working properly. Otherwise, it fails. Okay? So this is absolutely needed for this case. Another requirement is this voltage should larger than some fixed value for the proper operation of this. Okay? For that purpose, this value, this resistance is needed. Okay? All right. The current is determined by this side first. Then this current is determined depending on this current, and the relationship between them is CTR, which is device property of that. And this TL431 schematic of internal circuit will be discussed later. Okay, but that is called open collector type. All right. This is the schematic. This is actual schematic. We generate the hardware using this. We send this to some guy, and guy made the PCB for us. We soldered, and we made our experimental converter. Okay. So this is the flyback transformer. This is the diode, 2 diodes in one package, and we used 3 capacitors in parallel, and there is a jump. Okay. The usually jump should be connected for the proper operation, but this can be opened to measure the loop gain. Okay, we measure the loop gain and all the transfer functions with this setup. So we prepared this jump line to measure loop gain. Okay, and this is the structure. This is the device TL431. Some people is using this genodiode symbol. They are thinking this is just reference. It contains reference, but it's not a reference. Reference plus transconductance operational amplifier is the TL431. Okay. Anyway, 3 terminal device. This capacitor, and this provides the integration, and this resistor, and this capacitor is providing 1, 0, and this is the additional resistor I explained. This is optocoupler, and this is the capacitor to stabilize something. This is the current sensing resistor, and this is a gate drive circuit. Okay, fast turn on, controlled turn on and fast turn off, something like this. Diode is here, and this. Okay, all right. This is okay. And there are one resistor here. This one is important resistor. This is the design parameter. So you need to determine this. You need to determine this, and this gate drive circuit is just standard. Don't use the additional gate drive here. This is the cheap solution, cost-effective design. Okay. So avoid any fancy device here. So we are using this, and this is the protection, and this is the stabilizing capacitor. All right, and this is the optocoupler. All right. And this is the one additional auxiliary winding to provide the DC voltage here. Okay, and this VCC is stabilized this capacitor, and this genodiode is the protective diode for this voltage, and this is the control chip 8 terminal. Okay, this provide all the functionality for the peak color mode control, and these two are design parameters. This one and this one, and additional one. This one is to measure control to output voltage of control to output voltage transfer function of this voltage. Okay. So we are talking about this. This is we are using symbol of G, VD, duty ratio to output transfer function. It's very difficult to measure. This D is what? D is the digital signal. Okay. D is generate this pulse wave modulate gate drive signal. This is the digital signal, and the V is our voltage, continuous varying our voltage. So measuring this and this requires some skill. Okay. One guy long time ago, one guy developed digital modulator to measure the control to duty ratio to output transfer function directly. Okay. But only in the paper, nobody is using that. Okay. Theoretically, that is possible, but there is a way around to measure this indirectly. We measure control voltage to output, then control voltage is passing through this PWM, and the PWM gain is coming in the middle. So we measure control to output voltage, and we know the modulator gain very simply. Then using that result, we extract the transfer function from duty ratio to output voltage. That is the conventional way of measuring duty ratio to output voltage. You cannot directly measure. You can calculate this. Okay, you can calculate this, right? But in measurement, you need to deal with the digital signal in input and analog signal in output. So alternative way is measuring this control voltage, and it goes to this modulator. Okay, so you don't measure this. This gate drive signal is in the loop. Measure input output, and you extract this information. Okay, for that purpose we are measuring this. So this is additional OPM to implement the unit gain buffer, and we have additional power supply to provide the power here, but this is unnecessary. Okay, so there are several junctions here. Okay, so you connect the jump cable, disconnect the jump cable, then you can do the measurement or normal operation of this converter. This is the photo of the hardware. This is diode. Two diodes in parallel. Right? So this is output capacitor. Three of them in parallel. And this is the jump line. There are some jump line and the testing point. And this is the transconductance operational amplifier TL431. This is the optocoupler here. Optocoupler is shown here. Okay, this is the sensing resistor, and this is the design value. So this we should design this. So my student, they did many trial and error here, okay, to determine this. And this is the IC NCP something, NCP diode, and the gate drive circuit, and this is MOSFET. This is a transformer, and this is the bulk capacitor to stabilize this. All right. So we use the absolutely minimum number of components. Okay, and this is the extra element to measure the control to output transfer function. This is a standard operational MUA 7441. All right, and something to control this. Okay. This hardware. Okay, we used this to measure the various performance of this converter transfer function. To compare with that, the PCM simulation result and analytical predictions. Okay. Okay, I think this is the end of lecture 1. Lecture 1 is just the introductory discussions, explanations about this hardware, okay, and this the basic concepts of offline converter. In the Thursday, we'll discuss the topology and operation and some values and some waveforms of flyback converter. Okay, so they are very easy. Okay, because we discussed many times, and this the 3 times about the flyback converter. So next time we move fast, right? Okay. And next class, I'll explain how to get into the YouTube channel and homepage. Okay? I'll prepare some demonstration video to save time, right? Okay, we start here. Okay, thank you.